This conference will now be recorded.
All right, Tom, you want to start off?
Sure. Great. Thanks, Anish. Thanks, everybody, for joining. We're going to do another Grasshopper working session. Today, we're going to be focusing a little bit on what it means to study the environment and how that might be applied to projects using plugins like Ladybug and Honeybee. And to start things off, I put together sort of a slide deck that shows a sample project workflow and how you might envision starting a project or maybe even transitioning a project into a data-driven design approach using Rhino and Grasshopper, and what that might look like as examples and the output you might get. So I'm going to share my screen and run through this with you all. Please stop me if you have questions or—
Are you sharing your screen?
I'm sharing this screen.
There you go.
Look good?
Yeah.
Cool. So we're saying this is a project workflow potentially for simulation, data-driven design, and just by happen chance and sort of happy accident, all these models that you're making for simulation and data-driven design are typically primed for fabrication manufacturing technologies like 3D printing. So that's a fun plug. Dry, but we'll get to some of the more interesting imagery, is sort of a toolkit that we've developed in-house, or some things that we can do pretty rapidly for any and all projects using EPW weather data, Rhino and Grasshopper, and the plugins we're discussing today. Some things like temperatures in the environment. How do we feel as human beings when we're too hot and too cold, and what that means for places like Boston versus, we're going to show you, I think, Egypt today, like Cairo as a comparison. Thermal index goes along with sort of the environment and what it feels like. But we can study the sun's humidity, the temperature, its location, wind, and even things like rainfall. So it's like a sun, wind, and light environment simulations. This is something we're going to look at today called the Universal Thermal Index, and it's kind of this three-dimensional chart that shows you the climate in any designated place using EPW weather files. Some sun charts in terms of humidity and temperature, so you can now three-dimensionally track the sun and kind of make diagrams from that. Even locations of like a single point in time in a calendar year for where the sun might be located, if you want to be specific. Wind roses, broken down either by month or an overall annual aggregation. We can do this to sort of understand where the primary and prevailing winds are, or when they are in certain months. Rainfall collection, pretty simple stuff. Might be important for some parts of the world, but just knowing that it's available is sort of a cool thing. And then what do we do in terms of applying these technologies, or how do we do it, right? And so first and foremost, I'm saying that you're making a site context model. Understanding your environment and maybe your landscape is probably a really good thing to start with as you start to ramp up to design projects, either at the building scale or master planning scale. Developing your client criteria, all the way down through using the scripts is sort of a great thing. And we have all the software and tools in-house to do this. We're still interested in computational fluid dynamics. That's one thing that we don't have in-house, but if you're interested, definitely let us know. And what kind of deliverables and returns on the investment of making this sort of workflow a priority gets you some pretty interesting output. So as you're doing your simulation, you could also be 3D printing scale models at very large quantities of buildings if you want. This is a project that we did. The client criteria is sort of left blank on purpose, and that's just to say that every project needs are a little different, every client needs are a little different, and we can accommodate that if we can sort of fill this page with storylines and avenues of approach to help influence or to sort of clarify your design intent using data. And then again, project massings and getting actually into your project specific, while also having the context, which is really nice, and transitioning models into more complex geometries and using our in-house equipment. Understanding building form and what the sun is doing on an object, that's something that Anish is going to go over today. So it's more of a direct application of the environment and the sun on your building masses. This is a diagram from a company called SimScale, again, computational fluid dynamics in terms of studying wind in a digital tunnel instead of going to something like a physical wind tunnel, which many projects do. We can kind of take our first steps while looking at multiple options before ever taking anything physically to the tunnel and paying for that sort of solution. We can do that live while we design. Sunlight hours and understanding where the sun is and where it might not be. This is an example of an outdoor space for a full calendar year, noting where there's shaded areas or direct sunlight areas. Maybe you want to place furniture or a pool or something like that, or it's an amenity deck and you just want to study the way that the sun is interacting with the surface. Shadows, pretty self-explanatory, but very important. We can also do things like terrain analysis, highs and low spots, where water might settle. Maybe you want to start collecting rainwater, something like that. And even things like view corridors and preserving views from certain locations. And this can be on the ground plane like you're seeing in this diagram, or everything from inside a building looking outward into the city and what sort of view you'd see from there as a three-dimensional object. So then you could start to iterate and do those things all over again. You can do it on many design options that you're designing all at once, or you can, take the same design that maybe been improved and continue to work through these processes on elements of the building, down to sunshades or glazing systems, maybe even facade treatments, which again, Anish is going to share a little bit more of that later. So I'm going to stop sharing that screen, and just like a lot of our resources, you can find them on Emmy under the Grasshopper tab. We'll be posting this as well with some content, and all of the content today is in our project folder. So I'm just going to go through a really easy, I hope it's easy, idea of how to use one of these scripts. And I'm going to share my Rhino screen. And this is as if I've opened the template. It's completely blank. There's no geometry in here at all. There is just one layer called analysis, which we can use to sort of like bake, so to speak, what we're going to see visually in the diagram. So we can save it, and I'm going to compare it. So I'm going to make another analysis layer. And then opening Grasshopper, I've already opened Grasshopper and the plugin. So if you were just going to, go to File, Open, and open the Grasshopper plugin from our file structure, you'd be using Universal Thermal Index. The Universal Thermal Index script is pretty much completely pre-built, and there's only one input, which is an EPW weather file. Those can be downloaded from the link provided right in the script. So if you go to energyplus.net/weather, you could navigate to the closest, let's say, airport, for example. That's what we're going to use today for Boston. And that airport is taking real meteorological data from a duration of time in the past. And then we're able to use it as a sort of a conglomeration of data to call from to inform decision making for projections into the future. But it is important to know it is past data. It is important to know that it's a little bit different than just solar rays, as it is taking into account things like cloud cover throughout the year, and sort of averaging or aggregating that data that we can pull from as we want to use it for many things, one of which is studying the environment. So the only thing you have to do is double click the false toggle to go to true. And in our solar radiation project setup, there are EPW weather files already downloaded. And I'm going to use this USA Boston Logan International Airport, and it's a TMY3. And if you go to the website, again, Energy Plus, you can learn all about TMY data. There is text there that you can copy and put into your presentation documents. And it is sort of a government agency that's putting together the information. So it's sort of reliable in a way that you can feel good about the footnote you're putting in there. Teams have done that in the past for language. Open that up, let it run. Shouldn't take more than a few seconds. And here we go. And I'm just going to minimize my Grasshopper screen so we can see. I'm in a plan view. We'll go to 3D in a second. Sort of reading the months across the bottom. There's a temperature map in degrees Celsius, and behind here is times of day. It's kind of a little bit skewed, but we can see it in 3D. And it's telling me where I am and what I'm looking for. So I'm looking for the full calendar year and understanding the thermal climate index in degrees Celsius per hour. Three-dimensionally, you get sort of this really spiked geometry that you can start to understand what's happening throughout the calendar year. Understanding, we have a seasonal temperate climate, so we have summer and our winter months where we're typically cooling buildings here, for example, and we're heating buildings here. And everything in sort of the middle ground, which we can extract the hots and the colds, or where we're sort of comfortable as inhabitants in the city. So you can use this to start to describe HVAC programming or what times you're inhabiting certain projects, again, when the building might need heating or cooling, and I'm sure many, many other examples that I'm not going to be able to roll off the top of my head. Back over in Grasshopper, I'm going to go to the end. And the output here, again, sort of has a step 2. There's only 2 steps here. It says right-click and bake. So I will, and I'm going to put that on my first analysis layer and say, OK. I'm going to go to my second analysis layer and just hide what I baked. It's live now. I'm going to toggle this off and then back on. And I'm going to use this Cairo International Airport. Very different. Letting that run. And then again, I'll minimize so we can sort of see that output. So just as you'd probably expect, hotter and less blue, right? So this has gotten wider, and what I can do is I can turn on my old analysis and select those objects, and I can move that aside and now maybe start to compare the two. So it's much drastic temperature changes here in the city of Boston in the Z scale. A lot longer, wider time frame for like what would be considered too hot in the summer months, and obviously that's sort of what we'd expect. But now we can visualize it, and whether it's in isometric or it's in plan view, you can export all of these images to your drawing packages or presentations and use them to start conversation around environment, around data-driven design, and using tools like algorithmic aided design to inform decision making on a project, and to start really just opening up that conversation with your project team and your clientele. And with that, I'm going to stop sharing my screen, and Anisha is going to show you how to do a similar analysis using the sun on, I think, buildings.
Cool. Thanks, Tom. All right, so I'm going to start with just a blank Rhino environment that I have a box in. It's in feet. I just wanted to put like a nice little, how big is this box? I was trying to make a nice lab box. It's like 203 feet. Let's make it like 235. And then make this, a little, it can be whatever dimension it needs to be. But basically, so I'm just putting in a box that we can use as a nice little test object here. So I assign it as this geometry. Oh, I'm actually still running my solar analysis here. I should probably turn that on. Oops. Just a second. Okay, so I'm going to set this one geometry, but then I'm also going to contour it. I'm going to try to contour it and get the floor levels and sort of build like a nice little floor by floor model of this building. And you'll see sort of later on why I'm doing that, but basically I'm contouring at every 14 feet, making 14-foot extrusions, capping them, and then using solid union to put these all together. And I'll start from scratch here, and then you can see what I'm going to try to do with all of this. So if we just run the analysis, we put this object into the radiation analysis in the input section. I'll maximize so we can all see what's happening. When you open it, you'll have to add the EPW file the same way that Tom showed at the beginning. We input our geometry into step 2. Step 3, the default had 1 to 24, but I'm going to just do the time to be 9 to 17. So that's like 9 to 5, typical office hours, because I'm going to assume an office project for this box. And then, I mean, really, let's just run it and see what we have. Oh, and also, so the grid size. So I'm doing this in feet. So if I set my grid size to 7, we're using 7 feet. So I can actually, if I turn this on, you can start to see. Why am I not able to? There we go. So we can preview our geometry and see what we have. So you can see some sides are hotter, some are not. And you got a range of about 1,260 kilowatt hours to about 0 for some of the surfaces are completely shaded for the most part throughout the day, like this one that's probably just like a north facing. So what are we really getting at when we have this radiation analysis? We're getting a mesh that you can bake. So if we turn off preview for everything else, just look at this mesh. We're gonna have this nice mesh that just has colors that sort of tell us what's a hot surface, what isn't. But then we also have a result, which if I use panels and really look at this result, it's giving us kilowatt values at specific points. And if you go to test points here, you'll also be able to see the point of the analysis. So let's get a geometry thing and actually try to tease out all these test points, right? So it's testing at each single one of these points, what is the radiation value? And then it's making a tile, and that's defining the color of the tile, right? And for each one of these points, it's just this numerical value for the kilowatt hours, right? So if we had that legend on the side, you can see this legend is telling us the color is corresponding to that number, right? So once we have that number for all these points, we can start to apply that to our building geometry and start to alter it in different ways. You could use it for overhangs or window sizes. I'm going to show you guys how to do something with window sizes as just a sort of quick test. And for that, let's go back to the floor to floor elevations. So we have these extrusions. Let me turn off all the radiation analysis stuff for a minute here. So we have this building that's these faces, right? And before it's capped, it's just these 1, 2, 3, 4 surfaces. So what I'm going to do is I'm going to take something like Lunchbox that can panelize these kind of strips of geometry, these surfaces, and turn it into windows. So let's just take these extrusions. Oh, I think I need to explode the VREP, deconstruct VREP. Right, and so now we have 4 faces. We simplify 1 through 12 layers. That's 1 for each floor because we did our contours up like that, and then 4 faces for each one of those levels corresponding to each face. I'm just going to do it kind of quick with the UV because you could really specify based on the length, the V division, and all that stuff. But just to get through this really quickly, let's say vertically we're just going to have one nice panel per floor, but then going across, let's just say you got like 10 divisions, right? And if you really wanted to get, you'll see that it's sort of a different division. If you're trying to get more of a fixed distance, then you'll really want to calculate what is the length of each edge and actually start to make those lengths correspond to that. But let's just work with everything is divided by 10, right? So you have 10 panels for each floor on each face. And so each one of these panels has a centroid point, and we can get that centroid by getting the area, using the area module and getting the center point. right? So each one of these center points, now we can go take this over to all of our test points, right? All these test points and start to say, there's a command for closest point, right? Closest point, find the closest point in a point collection. So my point collection, if we just flatten this list of points, it's just, 4,150 points. That's our collection. And then for each one of these centroids, which one of these points is the closest, right? And this is going to tell us the point, but then it's also going to give us an index. So if we see what we're getting out here, we're getting a number. So it's saying the 3,930th point because we flattened this list. So if we go back to our list of points, we've got all these points. So it's saying go down to 3,930. It's somewhere in there, right? But that test result point also corresponds to our radiation result, which is, these values here. So if we want to say the point closest to this, what is the radiation value for that? We can now use list item, take this index, take this radiation result, and the result also needs to be flattened too, because it's just looking through, all 4,000 of them, just straight up, right? Just saying literally which one is the closest one. And it's going to give you a value. And so let's go look at these values that we're getting. So, a lot of them are 609, there's a lot of similar ones. I think there were also some zero values. Oh, there's no zero values in here. That's good. That means this is running properly. So so now that we have these values as saying each one of these points has this number, how can we start to manipulate the panel size? How can we start to make our windows a different size? If we look at the overall mesh, we can see that the range is up to like 1260, right? So we basically have to proportionalize this number and say, if it's a really high number, I want the windows to be smaller, so you get less radiation. And if there's a really low number, I want it to be big. So what I'm going to do is take the biggest number, or any number that's a little bit bigger than this. Let's say the biggest number is like 1260, right? So I'm going to use 1500, and let's divide all of these numbers by 1500. So we can say out of a maximum of 1500, how close are we getting, right? So let's see what we're actually getting here. We're getting, 0.4, 0.2, and so where you get bigger radiation values, you're getting smaller proportions out of one, right? Out of this, percentages of one. So now we can actually subtract this from one, right? One minus this. So we can kind of get this nice inverse relationship. And then let's go back to these panels. So Lunchbox has a really nifty offset panel frame command, right? So we take all our panels that we had before, all these guys, these square guys. I'll turn this radiation analysis off. Maybe all these tests, right? So we've got all our panels, and we want to slap some frames on it. And so it's looking for a scale factor between 0 and 1. So the bigger the scale factor, the closer it will be to the full size frame. So the smaller the number, the smaller the frame, right? So that means the way we've done our math here on the side, we can basically just plug that in, because now, where we have large radiation, or not that much radiation, right? This is 609, for example, for the very first ones, which is around the mid-range. So it's going to give it about the mid-range of the scale, right? And if you really want it to be, I'm doing it from like 1 to 0, but you can start to go between like 0.5 and 0.75 if you're really trying to be more subtle with it. But then let's plug that in and see what we get, and maybe turn off our previous stuff, right? So now all our frames are different depending on the radiation result, the size of it, the scale of it. So where on the north face you're basically not getting that much sun, you can actually start to have big windows. And now we can actually manipulate our model depending on the sun orientation, and it'll actually start giving us some different results, right? So you can start to see how things would change. But when you're doing just a flat face, obviously each elevation for the most part is going to be changed, especially when you don't have any context. I don't have context plugged into this model. I can actually plug them in. Let's plug some in and really see what that does. I just copied another block, and let's call that, so we already have it right down here, and that goes into this context guy, right? So we're just going to set this one brep, and it's going to recalculate based on if we have this building as a context object, right? So it doesn't really seem to change too much, but oh, you can start to see some differences here. But now let's twist this geometry and see what happens to it when you start to get different things to happen. Right, so you can see, oh, maybe I'll hide this too. So you can see as it's twisting, some of the windows are getting slightly smaller. It's starting to shift a little bit. If I twisted it even more, it would twist even more. It just depends on your ratios, but for any type of like solar responsive facade, this is like a good starting point to start to think about, you know, how should you adjust your range of outcomes depending on solar radiation and how you can start to vary it across a field. You know, this is changing every single one, but maybe you'd want it to be anchored to specific points. It just depends, but yeah, I think this is kind of just an idea of how to analyze make a more complex analysis and apply all that radiation to more complex geometries. And so I was making this out of flat faces because also Ladybug can't do curved surfaces with this radiation analysis. So it's really depending on straight lines that come into these flat planes and hit them. And when it's looking for a normal, right? So a plane has a normal, but when it's a bent curved surface, it just throws everything off for it, and you'll get really inaccurate results. So whatever analysis geometry, you always have to put flat fractalized surfaces in. So that's why even when I twisted, I wanted to use flat faces. But yeah, any questions?
That was cool. I had no idea that that was what you were going to show.
Yeah, right. And then you can even like move this a little bit.
Yeah. So homing in that point a little more about these are built sort of in the front end, so you don't have to think about building all that stuff that Anish was seeing in the red box. Taking and extracting the information that you get from the algorithm and then applying it is where that blank slide where it said like, you know, what the client expectations were or services, that's where you fill that information in. So Anish made up this really cool example of an application of a solar responsive facade using a twisted box. That might resonate with you 100% or more like 1%. But whatever your intended outcome is for taking something like radiation or sun hours or wind to apply to your project, we can start to create that dialogue together and start to understand the data from the outputs, which we can see in the script. What do we have to do with them now? How do we manipulate them and then apply them back to something like your geometry or your element? So these aren't complete out-of-the-box solutions for something that you're going to say, great, now I can just put this in my presentation. It's still developing that storyline and maybe working with, you know, our team to figure out how to get there if you're not as super savvy in Grasshopper as someone like Anish is. So we were just doing a study the other day where we were looking at sun on a ground plane again and trying to hit a target percentage over the course of a duration of time on a very specific day. And that storyline was shared with me, and then we were able to take again one of these existing scripts and build it out to find percentages across an average sample, which is what Anish was showing with those sample points. using all the stuff that comes right out of the back end of one of those ladybug components.
Right, and this doesn't have angle, but if you were trying to do like overhangs, you could do solar angle and start to, instead of getting, like I'm getting a number value for kilowatt hours, but you could really start to say what is the most common sun angle that's hitting this facade, and then optimize the angle of your solar, shading for that. There's a lot of applications for it,
Right.
depending on which tool you're using.
Other applications, we're studying the face of glass on a building, and what can you do with greater reveals or adding sun shading geometry, horizontal, vertical positioning, and what that does to the glass and also potentially the interior floor plane on a very specific space within your building project. So whereas Anish, again, is looking at a full building, we could look at a full master plan and start to inform the shapes of buildings to have them color properly in a way in the heat map. And as you target some of the orange and middle ground colors, you start to see more of a balance with that too hot to too cold ratio. But again, you could go all the way down to a finite element like a vertical sunshade or something like that, or something I'm not even thinking of, but interesting.
So you could take the angle of the sun that's coming in and maybe use that to figure out how deep to make a sunscreen, like that was maybe projecting straight out.
Yeah, you would just find it just depends on what you're targeting, because sometimes you'd really want I think for a lot of overhangs, you pick like your worst angle, like your worst time of day angle for like the sun or something, because sometimes you actually want, like in winter, you want like the sun to come through. It's just kind of just finding that optimum angle.
That's right, and you could probably run two scripts simultaneously, one looking at winter solstice and the other looking at summer solstice, and optimizing that angle or the depth from face of building. Also, maybe what a density pattern for something like bar grading. If you're going to get cute with bar grading and use it as a sunscreen, what's the density of the grading? And you can sort of model that and see what its live impacts are for something like sun. Pretty powerful. And once you do that, you can start to get into more custom designs too, right? And understanding that not all pieces have to be necessarily the same angle or the same geometry or off the shelf. So what if you want to do like a perforated metal because you like the way that looks, but you want the perforation to be derived from the sun and create a custom pattern. And there's a nice story there somewhere. And that's all achievable this way.
Awesome.
Cool. Yeah, I mean, that's pretty much all I had.
Yeah, that's all I had too. Again, there's plenty of samples of this, and we're going to be, you have access to that sample project workflow in the same folder. So if you want to look through that a little bit, and if any of these topics are interesting to your project design workflow, definitely reach out. And if you're not familiar with how to use the tools, or but you really still want to get involved, we do provide hands-on training, one-on-one training, or even project-specific application where we could assist you through the process on a deliverable for a project client deadline.
Yeah, and I think maybe the next time we try to get to the daylighting or something, that might be another topic we come to next. Should be interesting that we can build on this.
Yeah, I know Bohan has been working really hard on daylighting analysis algorithm. I've had the honor of sort of beta testing it with him, and it's coming along. So yeah, we'll be going live with that one sometime in the near future.
It'd also be fun to see like a project that's already underway, and see sort of like what some of the, now that we're sort of getting some of the baseline ideas out of what is possible, taking a real project and applying some of these techniques and see how they affect, change.
Mhm.
That'd be-
Yeah, I have at least a handful of examples, probably half a dozen to a dozen. Does anybody know the protocol for something like that, for like project sharing? I guess I should reach out to the project manager and make sure that that's something that's able to be shared in a group setting like this.
In terms of confidentiality for clients, or what?
Correct. Correct.
Yeah, if the project isn't set up to be confidential, yeah, it's always a nice courtesy to ask the project manager, but if it isn't a confidential project, it shouldn't be a problem.
Yeah, I mean, I have a project that I could share honestly right now. I'm just not sure if it's appropriate. But
I can tell you if the project number is confidential.
19054.
Okay. Does not have special security applied to it. What's the name of the job?
National Landing.
Yeah, I mean, it's always a good idea to run it by the project manager first, but I mean, that potentially could be shareable from what I can see.
Yeah, well, at least let me show you at least one image. It's sort of nondescript anyway, and I can describe what we were doing and what the data told us, and then what the outcome of that study was. All the images are pretty much the same, just the design changes, and I think you all can visualize exactly how that happens. Bear with me for just 1 second. There we go. Okay, so this is a chunk of context and some proposed buildings, and the analysis plane we're looking at is this open space in the middle of town. The open space has requirements for a specific percentage of direct sunlight across the average surface between a 4-hour duration on one of the equinoxes. So we know the time frame, we know the date, we know the geometry in question is all context, and the analysis plane is that flat ground plane. This is a script called sunlight hours. It's sort of the inverse of a shadow study in a way, but it will show you kind of in the yellow where you get complete direct sunlight compared to something like the blue, which is sort of the 0 value. So 4 is yellow, 0 is blue. There are, I think, 9 different scenarios that we went through, all changing the proposed designs. And the idea was to take the sample points in this 3 foot by 3 foot sample grid area, extract them into that percentage. And that's basically a total aggregation, a mass addition, and then a division by the number of sample points will give you sort of an average across the field. And then you convert that average into a percentage. So if we were going to say that there's an existing scenario and then a modification, and there were 7 design options that came out of a study, a design study, a design charrette, then we went through an analysis post that design charrette. So we took 7 options, put them through, and at the end of the results, I can say that 3 of 7 passed the criteria for the percentage of direct sunlight on this area. With that being said, if you are using the algorithms live, like Anish was using them, or if you're doing these sort of sunlight studies as you design, you can be sure that all 7 of your design options will meet the percentage requirements on something like this before you ever take the time to make 4 and then have to realize that maybe some of them don't meet all the criteria.
So a little bit of work up front saves you time from going down a road that doesn't really get you there. Right?
Precisely. And that sample project workflow should fine tune your upfront project geometries to be able to do studies like that pretty rapidly. One of the greatest things that I've seen in my experience is that project teams want to now do a study, or they've been prompted to do a study. It's a requirement, and they have to transition their entire project from a different software platform, clean it up to something that's more solid models for data simulations, and then get to the scripting. And you know, in my experience, again, like 80% of the work is the conversion of the model, and the other 20 is you know, getting involved with the storyline, and then finally just running the script and exporting drawings. That doesn't take much time at all if the project's set up in a way that Ladybug and Grasshopper can identify objects.
Great.
Cool. Well, yeah, that seemed pretty straightforward and to the point. Thanks again for everybody who's joining us. If you have questions or comments, now would be the time. Otherwise, let us know if it pops up in your mind later.
Okay. Really appreciate you taking the time to prepare this to be presented. I mean, it really is good for opening our eyes and making us, you know, keep that running in the back of our heads, and you know, think about similar things, or you know, if somebody else mentions a project that needs it, it's just good to know that that's available.
Wonderful.
Thanks, guys. It's really good work.
Thanks, Chad.
That's it.
All right. Well, I guess until next time, thanks to you all, and take care until we see you.
Thanks, everybody.
Thank you.
Bye-bye.